the membrane is now 35 millivolt plus 35 millivolt, and it is fully depolarized. When this level is reached, the voltage gated sodium channel starts to close and they become inactivated. We have talked earlier about this. When the voltage membrane potential reaches plus 35 millivolt, the sodium channels become inactivated. So sodium entry decreases. At this time, the potassium entry increases because of the opening of the voltage gated potassium channels. As we have talked earlier, that the potassium channels, voltage gated potassium channels, open slowly and then remain open for a long time and then close slowly. So as the sodium channels are closing, the potassium channels are opening. So the influx of positive ions stop and the efflux of positive ions start. So now the membrane which was depolarized, that is the membrane, the interior of the membrane which was positive, now starts to become more negative. That is, it starts to go towards zero. So we see that the sodium influx decreases and the potassium efflux increases. So the net effect is negativity inside the cell. The membrane thus starts moving from plus 35 millivolt towards zero. This is where repolarization starts. So as you know, what is repolarization? Repolarization is nothing but the recovery of a depolarized membrane. In polarized membrane, what was the charge? In polarized membrane, the charge was negative inside, positive outside, polarized. In full depolarization, what has happened? Inside is positive charged, outside is negative charge. This is plus 35 millivolt. Now, in repolarization, these inside positivity starts becoming negative again. Okay, so this is recovery of the depolarized state, is known as repolarization. Okay, the membrane is again becoming polarized. So the membrane potential starts to recover and move towards zero. This is where the repolarization starts. Now, there is movement of positive charge outside, hence the membrane becomes more negative and repolarization occurs. Initially, the repolarization is a fast process due to rapid exit of potassium. This is known as rapid repolarization. Why rapid exit? Because of the electrical gradient. Okay, so there is rapid exit of potassium leading to rapid repolarization. But as the interior becomes more negative, the efflux of potassium slows down. Initially, there was high electrical gradient, but as the electrical charge inside the cell is becoming more negative, this electrical gradient was decreasing. So the efflux of potassium slows down. This is known as after depolarization. Since the potassium channel closure is slow, the potassium efflux continues for some time after the membrane potential has reached the RMP level. This leads to after hyperpolarization, where the membrane potential becomes even more negative than the resting membrane potential. This is known as after hyperpolarization. Okay. Then finally, the potassium channel stops and the sodium channels change from the inactivated state to the closed state. And finally, the membrane potential reaches back to the resting potential levels, and ionic status is restored by sodium potassium ATPase pump. the sodium potassium ATPase pump is triggered by excess sodium inside and excess potassium outside. So we get starting of repolarization, then rapid repolarization, then after depolarization, followed by after hyperpolarization, and finally the return of the membrane to the baseline resting membrane potential value. Now the closure of the potassium channel is basically by negative feedback. We just saw a little bit earlier that the opening of the sodium channels was by positive feedback mechanism. Here we see that the closure of the potassium channel is by negative feedback mechanism. Let's see what is the negative feedback loop. See here. This is the negative feedback loop. We have depolarization of the membrane by sodium influx. This leads to slow opening of the voltage gated potassium channels. Then when finally the voltage gated potassium channels open, the permeability of potassium increases. This leads to increased flow of potassium out of the cell, that is efflux of potassium. This occurs during the rapid repolarization phase. This leads to repolarization of membrane potential. This repolarization of membrane potential, that is the membrane potential becoming more negative, inhibits the further opening of voltage gated potassium channels. Because the voltage gated potassium channels opened as a result of the membrane becoming more positive. So if the membrane becomes more negative, then the opening is inhibited. So in this negative feedback loop, efflux of potassium inhibits further opening of the potassium channel. Okay. Now some more important points. One is that during a single action potential, there is not much change in the concentration. That is, there is only a small change in the ionic concentration. Significant changes in the ionic concentration is seen only after repeated stimulation. We did say that when sodium moved inward, the concentration gradient decreased, but it was very minor. Okay. Now another thing we need to know is the effect of extracellular ions on the action potential. We have previously learned that extracellular sodium has no effect on the resting membrane potential but has effect on the action potential. And extracellular potassium has a huge effect on the resting membrane potential. So what happens in decreased ECF sodium, when extracellular sodium, that is serum sodium, decreases, that is, this is known as hyponatremia. Okay, serum sodium decreases, hyponatremia. The action potential magnitude also decreases, but there is no effect on resting membrane potential. Okay, action potential decreases because this action potential occurs due to explosive entry of sodium. If sodium is less sodium will enter and we will get a lesser response. But in resting membrane potential, sodium has a very small role, therefore it doesn't affect the RMP much. Now coming to potassium, if the extracellular potassium increases, the concentration gradient becomes less and the membrane potential becomes less negative inside. So the membrane potential moves towards the firing level and the membrane becomes more excitable. The opposite happens when the serum potassium decreases. This is known as hypokalemia. Increase in serum potassium or increase in ECF potassium is known as hyperkalemia, which makes the membrane more excitable, and decrease in serum potassium is known as hypokalemia. Here what is happening? The concentration gradient is changing and we get a more negative membrane potential. As a result, the membrane moves away from the firing potential and we get hyperpolarization followed by a less excitable cell. Okay. And what was the effect of calcium? We have already learned that if calcium increases, we get a less excitable membrane. That is, in hypercalcemia, we get a less excitable membrane, and in hypocalcemia, we get a more excitable membrane. Okay. So to summarize, this is the action potential. This is the action potential. This is the permeability of sodium, and this is the permeability of potassium. In sodium, there is a fast rise and fast fall, while in potassium, it is slow rise and slow fall. So this is the latent period, this is the firing potential, this is the rapid upstroke of depolarization, this is the spike, this part is the rapid repolarization, this is the delay, this is the after depolarization, this part is the after hyperpolarization, and finally it comes this restoration of the membrane potential. Okay, so we now know what is action potential and what is the role of the ions in development of this action potential. And we have also discussed what is the state of the channels when the sodium and potassium ion channels open and close and become inactivated. Now we will talk about the refractory period. Let's discuss about refractory period. After application of one stimulus, a nerve fiber does not respond to another stimulus for some time. This is known as refractory period. That is, after it is stimulated by one nerve, it becomes refractory to the effect of another stimulus. The first stimulus comes and forms an action potential. Now the next stimulus comes, but it cannot form an action potential for some time. This period is known as refractory period. Now refractory period can be divided into two parts. The absolute refractory period, which is known as ARP, and the relative refractory period. It is known as RRP. Okay, we'll just study the differences between this what is absolute refractory period and the relative refractory period. Okay, so in absolute refractory period, during this period, the membrane won't respond to stimuli no matter what the strength of the stimuli is. Okay, during this absolute refractory period, the membrane, even if we give a suprathreshold stimulus, the membrane won't respond. No matter what is the strength of the stimuli, the membrane won't respond to any stimuli. Whereas in the relative refractory period, if we give a suprathreshold stimulus, the membrane will respond. Okay. Now, the absolute refractory period is from the starting of the firing potential to 1/3 of rapid repolarization. Okay, firing potential to 1/3 of rapid repolarization. Now, the relative refractory period is from 1/3 of repolarization to the start of after depolarization. Okay, so after rapid repolarization, we get after depolarization. So here the relative refractory period is from 1/3 repolarization to start of after depolarization. This absolute refractory period occurs due to inactivation of the sodium channels. As we have talked earlier, in inactivated sodium channels, the inactivation gate closes and the activation gates remain open. In this state, it becomes refractory to any stimulus. No matter how much strength of stimulus you give, the channel won't open. Okay, so this due to inactivation of sodium channels, we get absolute refractory period, because if the sodium channels won't open, there is no question of development of any electrical impulse, any electrical change. That is no question of development of action potential. So due to inactivation, we get an absolute refractory period. Whereas during the relative refractory period, the sodium channels have started to recover. They have started to be reset from the inactivated state to the closed state. And as we have discussed, the closed state can respond to a can respond to stimuli. So if we give suprathreshold stimulus, that is more stimulus, more number of sodium channels will be reset, more number of sodium channels, closed sodium channels will open and may give rise to an action potential. Okay. So we see what is the difference between the absolute refractory period and the relative refractory period. These refractory periods keep the action potential discrete and meaningful. They prevent the action potentials from overlapping. Okay. So now coming to the electrotonic potential and the local response. What happened if we give a stimuli to an excitable cell? If we give a stimuli to an excitable cell, initially we get an electrotonic response, which will give rise to local response. If the stimulus is threshold stimulus, initial stimulus was threshold strength, the local response will change to action potential. But if it was subthreshold stimulus, what will happen? The local response will dissipate. This action potential will then propagate to other parts while this local response dissipates and does not propagate. Okay. So now coming to electrotonic potential. What happens in electrotonic potential? Let me show you a diagram. See here. In electrotonic potential, there is passive change in membrane potential due to application of stimulus. I'll explain. Just see the diagram first. Here is minus 70 millivolt. This is the resting membrane potential. This is the nerve fiber. We apply a cathode and an anode on the surface. This is the external surface. We apply a cathode and an anode. Okay. So for cathodal stimulation, we get the membrane cat electrotonus. Okay. So the membrane becomes less negative. And if we apply an anodal stimulus, the membrane will become more negative. This is known as an electrotonus. So electrotonic potential can be cat electrotonus due to cathodal stimulation or an electrotonus due to anodal stimulation. Okay. So this occurs due to passive movement of ions. We put a cathode, there is some passive movement of ions which leads to change in membrane potential under the electrodes without participation of the membrane. What is happening? We apply an electrode, this carries electrical charge, then there is passive diffusion of these electrical charge to the membrane. Okay. So the membrane was initially minus 70 millivolt. This passive charge, this is basically cathodal. I am talking about cathodal. Okay. So for cathodal stimulation, there will be passive diffusion of charges to the membrane and the minus 70 millivolt will go to minus 63 millivolt, that it becomes less negative or more positive. This is known as cat electrotonus. If we apply an anode, so cathode is positive charge. Okay. An anode, what happens? There is diffusion and the membrane goes from minus 70 millivolt to a more negative value. So the value can be anything from minus 70 to minus 80 millivolt. So it becomes more negative. This is known as an electrotonus. So what does cat electrotonus do? Cat electrotonus decreases the threshold and makes the membrane more prone to stimulation and action potential formation. While anelectrotonus, what happens? In anelectrotonus, the membrane becomes less prone to stimulation, leading to action potential due to lowering or due to increase in threshold. Okay, so a cathodal stimulus is more effective since it carries the membrane potential towards the firing level, while an anodal stimulus is not very effective because it carries the membrane potential away from the firing level. Now we see this here. What is happening? There is passive diffusion. There is passive diffusion of ions. So that means there is no active participation of the membrane. So electrotonic changes are due to passive diffusion, and in electrotonic changes there is no active participation of the membrane. And a cathodal stimulus or cat electrotonus carries the membrane potential from minus 70 millivolt to minus 63 millivolt. So what was electrotonic potential? It is basically the change in the membrane potential from about minus 70 to minus 63 millivolt due to passive movement of ions from the cathodal stimulating electrode to the membrane. So the membrane didn't participate in anything. You put in the cathode to stimulate the membrane, and the cathode gave some ions which moved from the cathode to the membrane and changed the membrane potential. Okay, so this electrotonic potential takes the membrane from minus 70 to minus 63 millivolt. We have talked about that the cathodal stimulus is much more effective than an anodal stimulus in creating an action potential. So we are mainly concerned with the cathodal stimulus. Okay, so a cathodal stimulus takes the membrane potential from minus 70 to minus 63 millivolt, and from there a local response starts. So see, for local response, look at this graph. Okay, sorry, let me change this. So now let's talk about the local response. What is a local response? Local response is a change in the membrane potential up to the firing level, that is from minus 63 millivolt to minus 55 millivolt after a stimulus with active participation of the membrane is known as local response. Okay, so what is it? It's just a change in the membrane potential from 63 millivolt to minus 55 millivolt. Okay, this is called local because this is a localized phenomena, and a local response is not propagated. A local response dissipates unless it reaches the firing threshold and gives rise to an action potential. Only an action potential is propagated. A local response is not propagated. It occurs locally on the membrane. Okay, now let's look at this graph. Look at this diagram. S1 is a stimulus of this S1 is a stimulus whose strength is less than S2, whose strength is less than S3, and this strength is less than S4. S4 is the threshold stimulus, it is the maximum stimulus, and S1 is the minimum. In this series, S1 is the minimum and S4 is the maximum. So This is the resting membrane level minus 70 millivolt, and this is the firing level minus 55 millivolt. When we stimulate a nerve fiber with S1 strength, we get a local response. This is an electrical activity or change in the membrane potential. This is a small change in the membrane potential. It rises and falls and dissipates. Now we give S2 strength. We get another local response, that is an electrical change of the membrane potential, which is slightly higher than the first local response, but it still is below the firing level. Now we give another stimulus which is higher than S2. Here also we get a local response which is larger than the second one. It rises and falls and dissipates. It is still lower than the threshold potential. Now we apply the S4 stimulus, which is basically of the threshold strength. Now this membrane potential reaches the firing level, and then it gives rise to an action potential, which is then propagated. So from here we see that when we stimulate a membrane, the electrotonic potential takes the membrane from minus 70 to minus 63 millivolt. Okay. Then after minus 63 millivolt, the electrical changes which occurs are known as local response. Okay. This occurs from minus 63 millivolt to minus 55 millivolt. As soon as minus 55 millivolt is reached, we get the action potential. Okay. So first, there is no involvement when we give a stimulus. There is no involvement of the membrane. This occurs from minus 70 millivolt to minus 63 millivolt. This is just due to passive diffusion of ions. Then the membrane involvement starts and local response is created, which takes the membrane from minus 63 millivolt to minus 55 millivolt. Okay. And then when minus 55 millivolt is reached, we get an action potential. If the strength of the stimulus is less than threshold stimulus, then the local response will not reach minus 55 millivolt. Okay. The local response will only reach from minus 63 to minus 55 millivolt if the strength of the stimulus is of threshold intensity. Otherwise, for a sub-threshold stimulus, the local response, we will get a local response from minus 63 millivolt. There is some change in membrane potential beyond that, that is the membrane becomes more positive and then it dissipates. It is localized, it is not propagated. We only will get an action potential when a threshold stimulus is applied. Okay. So why is this occurring? When it is happening due to the electrotonic changes, the membrane potential goes from minus 70 to minus 63 millivolt. This results in opening of some voltage gated sodium channels. Okay. This leads to further change in membrane potential, finally leading to development of the local response. So up till here, this was a passive process. Now, due to opening of the sodium channels, this becomes an active process. Here, there is no involvement of the membrane. Here, due to opening of the sodium channels, there is involvement of the membrane and it becomes an active process. So, the main thing to remember is that local response occurs due to active participation of the membrane. Now, local response takes the membrane from minus 63 millivolt to about minus 55 millivolt, and finally firing potential is reached and we get an action potential. Now, if the strength of the stimulus was not strong enough, this minus 63 millivolt would not go to minus 55 millivolt. The local response will take the membrane potential from minus 63 millivolt to minus 55 millivolt only if the strength of the stimulus was of threshold intensity. Okay, so this another thing I have said, why is this called local response? Because it is non-propagating. It develops and dissipates at the same point of the membrane, at the same point in the membrane locally, unless an action potential is generated. So also we see from the diagram we have discussed earlier that the magnitude of the local response depends upon the strength of the stimulus. So the magnitude is proportional to the strength of stimulus. And as a result, this is known as a graded response. Okay, this is a local response, non-propagating response. This is also known as a graded response because with increase in magnitude, with increase in strength of the stimulus, the magnitude increases. This is only true for when the strength of the stimulus is below threshold stimuli. When the threshold stimuli is reached or the stimuli is of threshold intensity, then action potential is generated and the magnitude remains the same. Okay, so understood the difference between a graded response and an action potential. With action potential, the magnitude does not change with the strength of the stimuli, but with a graded response, that is the local response here, the magnitude changes with the strength of the stimuli. Okay. So to summarize, all local response does not give rise to an action potential. Okay, depending upon the stimulus, all local response does not give rise to an action potential. Only if the stimulus is of threshold strength, an action potential develops. But action potential is always preceded by a local response. Okay, understood? So an action potential always arises from a local response, but a local response does not always give rise to an action potential. Now a local response has different names in different tissues. Local response in synapse is known as excitatory post synaptic potential or EPSP. The local response in myoneural junction. Myoneural junction is basically the neuromuscular junction, the junction between a nerve and a muscle. It is known as end plate potential. It is the EPP. The LR in a receptor is known as receptor potential. Okay, so a local response is also known as a graded response, and in different tissues it has different names: excitatory postsynaptic potential or end plate potential and receptor potential. Okay, you will be taught about these in details later in the later chapters. Okay, just know the names for now. Now let's discuss the difference between the local response and action potential. You already know them, but just to summarize them, let's go on to the differences. Okay, so the difference between the action potential and local response. Local response is basically the change of the membrane potential towards the firing level. It is from minus 63 millivolt to minus 55 millivolt. While the action potential is change of the membrane potential and complete depolarization. That is up to plus 35 millivolt. In local response, the size depends on the strength of the stimulus. As we discussed, this is a graded response and the size depends on the strength of the stimulus. But action potential follows the all or none law, and it does. The size does not depend on the strength of the stimulus. A supra threshold stimulus will not produce a larger action potential. Okay, so the local response does not follow the all or none law, while the action potential obeys the all or none law, provided all the other conditions like the ECF, sodium, temperature, etc. remain normal. Okay, next is the local response can even be caused by a subthreshold stimuli. Here the local response will form and dissipate and won't give rise to an action potential, but an action potential is only formed by a threshold stimulus. Okay, a local response can be summated, that is, many local responses can occur and be summated together to give a larger response, while an action potential are discrete and cannot be summated. Okay, and finally local response remains locally and action potential is conducted or propagated along the membrane without any change in size. Okay, so this is the difference between the local response and the action potential. Now let's go on to the conduction or propagation of action potential. When an action potential is formed, the electrical disturbance is propagated in all directions along the membrane. This propagation occurs a little differently in myelinated and unmyelinated cells. We will be talking about unmyelinated cells here. I will tell you what happens in the myelinated cell, but in short, because you will be taught about that when you do CNS in the later months. Okay, so this is a unmyelinated cell. What happens in a polarized state? We have talked about this. The inside is negative and the outside is positive. This is a polarized nerve cell. The inside is negative, the outside is positive. Now a stimulus is given. What do we give? A depolarizing stimulus, okay, by a stimulating electrode. Okay, so we give a stimulus, depolarization occurs and the inside becomes positive while the outside becomes negative. Okay, so in depolarization there is reversal of polarity. Now see, this is negative outside, this inside is positive. So now the adjacent areas are all positive, but this stimulated area is negative. So charge will flow from the positive areas to the negative area outside and from the positive areas to the negative areas inside. Okay, so this leads to formation of a current sink. This whole thing is basically a current sink. That is, current is coming from that current or charge is coming from the positively charged area to the negatively charged area. So on giving a stimulus, the outside becomes negative, positive, from positive to negative, and the adjacent positive areas allow the movement of charge to this negative area. Okay, because a negative area draws in charge, therefore it is a current sink. Here the negative area draws in charge, this is a current sink. Here nothing was occurring because this was all positively charged, this was all negatively charged. As soon as this charge is changed, there was development of a current sink. Okay, so what is happening when positive charge is flowing from this area to the original first area, from the second area to this first area, from the second area to this first area, this will become less negative and this will become more negative. Why? Because this is a negative area, positive charge is flowing, it will become less negative. This is a positive area, positive charge is going out, therefore it will become more negative. So this part will become more negative and this part will become less negative. Okay, since this part becomes more negative, ultimately what is happening? So if this part becomes more negative, similarly this part will become more positive. Actually what is happening? Up till now we were all discussing about the changes in the inside. Now you have to understand that while discussing the propagation, we are discussing the changes outside. So whatever we have discussed here, this will be just the opposite of that. What was happening in the inside? When the inside was becoming more positive, a local response develop due to opening of the sodium channels. So what will happen on the outside? The outside, when the outside becomes more negative, the action potential will develop, or the local response will develop, which will give rise to an action potential. Okay, understood? This is just the opposite of what we have been discussing. We have been discussing the interior, now we are discussing the exterior to understand the propagation of an epi. Okay, so this outside becomes more negative, this gives rise to a local response. And here, so we see a new area of negativity is formed, a new current sink is formed. This new negativity moves to the other areas along the membrane in all directions, and these in turn form current sinks. So, initial negativity was here, current sink was formed, the adjacent areas became more negative, local response formed, and these new areas, the adjacent areas became negative. Now in the same way, another current sink is formed, the areas adjacent to the second area becomes more negative and another current sink is formed. So current sink forms, then the adjacent areas become negative, give rise to an epi. Current sink forms, adjacent areas become negative and give rise to an local response and action potential. This is all on the surface. Opposite happens on the inside. Okay, so to summarize, what is happening? Normally, the outer surface of the membrane is positive and the inside is negative. When an action potential develops at one point due to a depolarizing current, the outer surface becomes negative locally and the inner surface becomes positive. This negativity now causes the positive charge to flow from the adjacent areas to it. Okay, so current sink is formed. On the outside, the adjacent areas allow the movement of positive to the negative area, and opposite thing happens in the inside. Okay, so on depolarization, this becomes positive and this leads to movement of positive charge to the adjacent areas. Okay, so this is the current sink formation, and due to current sink formation, the adjacent areas now become negative on the outside and give rise to an action potential. Okay, so as the action potential is formed on the adjacent areas, the first site undergoes repolarization. Okay, so first stimulus is given, action potential forms, becomes negative, current sink formation, the adjacent areas become more negative, the adjacent areas now gives rise to an action potential. Now the first area, which was previously depolarized, starts getting repolarized. Okay, so this was negative. After current sink formation, this two areas, adjacent areas becomes negative and the initial point becomes positive due to the start of repolarization. Okay, now these new areas of action potential in the adjacent areas will give rise to their own current sinks. This was the current sink, first current sink. Now these are the next current sinks. Okay, so this way the current sinks will propagate in all sides, giving rise to action potentials. So we see that discrete action potentials are formed and they are propagated in all directions. Okay, so this is moving this way and this is moving this way. Okay, so the action potential is moving this way and action potential is moving this way. Now can they move back? They are moving this way. Can they move back this way? No, they cannot move back because the membrane becomes refractory. We have talked about this. Due to the refractory nature of the membrane, due to the feature of refractory period, the membranes do not propagate action potential in the opposite direction. Okay, action potential is moving in this direction, but it cannot move in the backward direction. Okay, now what happens in myelinated fibers? We were talking about unmyelinated fibers here. Now let's go on to myelinated fibers. This will be discussed in details later. Okay, what is myelination? Myelination is just a myelin. Okay, so the myelinated nerve fibers have this myelin sheath covering them, and the small unmyelinated portion between two myelin sheaths, that is the junction between two myelin sheaths, is known as nodes of Ranvier. Okay, nodes of Ranvier. these have a high concentration of sodium channels. Since they have a high concentration of sodium channels, their threshold is very low and these areas are very excitable. Here, the action potential jumps from one node to another. Okay? In an unmyelinated nerve fiber, you saw that there was a continuous process, continuously, uniformly, they formed action potential in different directions. But here, the action potential just jumps from one node to another. Okay, one node of Ranvier to another node of Ranvier. This is known as saltatory conduction. Okay, jumping action potentials, these are known as saltatory conduction. Okay, you will learn about this in details when you do central nervous system. Okay, now let's talk about biphasic AP, biphasic action potential. Till now, we were measuring action potential by putting one electrode inside and one electrode outside of the membrane. By that method, we got a monophasic action potential. That is, if we consider this to be the baseline, the action potential was in only one phase, that is in only one direction. Okay, so this was the conventional method, by putting one electrode inside and one electrode outside. Okay, now the electrode inside initially showed negativity with respect to the outside, then it showed positivity, then again it returned to its original negativity. Okay, now what is biphasic AP? Biphasic action potential? We get the biphasic action potential when both the electrodes are placed on the outer surface of the membrane. Okay, so let's see how we get the biphasic action potential. This is a nerve fiber. Both electrodes are placed on the outside surface and connected to a CRO or cathode ray oscilloscope. As we have seen that the outside at rest is positively charged while the inside at rest is negatively charged. Now you give a stimulus, a depolarizing stimulus. Due to this depolarizing stimulus, the inside becomes positive and the outside is negative. But our recording electrodes are here. Here we do not get any change. Okay, stimulus is given, action potential is formed here, but here under the first electrode and the second electrode we do not get any change, hence we get a baseline recording. Okay, baseline recording. Now in the next step, the action potential has propagated and reached the first electrode. As a result, the area under the first electrode has become negative, which is on the exterior surface. Okay, this area has become negative. So this records a negative potential with respect to the second electrode. This is the first electrode. This is the second electrode. And the first electrode records a negative potential with respect to the second electrode because of this action potential. So the recording we get is an upward deflection or positive wave. So we are getting a negative potential recording but an upward wave. Why upward or positive wave? This is because of the convention that if the depolarization is moving towards the electrode, we will get a positive wave. So what is the convention? If depolarizing wave is moving towards electrode, we get a positive upward wave. But if the depolarizing wave is moving away from the electrode, recording electrode, we get a negative wave. We will just see where we will get this. Okay, so again coming to this, action potential has reached the first electrode. The area under the first electrode has become negative. We get a negative potential recording and an upward deflection because of the convention. AP is moving towards the first electrode, so we get an upward deflection. Okay, now the AP has passed this first electrode and has come at a point in between the first electrode and the second electrode. This is the second electrode, this is the first electrode. Now, as the action potential has moved here, the area under the first electrode has started repolarizing. Okay, it has gone through the repolarization phase and is positive again. Okay, so this is positive. First area under the first electrode is positive, area under the second electrode is positive. So the recording, the wave will return to the baseline. Here it was baseline, here we get an upward deflection, then again returns to baseline. See, baseline, upward deflection, then again return to baseline. Okay, now next step, what is happening? This action potential has reached the second electrode. It's the first, this is the second electrode. So the action potential has reached the second electrode. Now the area under the second electrode is negative. So what will the first electrode record? The first electrode will record a positive change. Okay, positive potential. Here it was a negative potential. Here we get a positive potential because the first electrode we are basically recording with respect to the first electrode. The first electrode is positive with respect to the second electrode now. Because of this, we will get a downstroke. Okay, see, we get a downstroke or a negative wave. Why? We get a positive potential but a downward slope. Why? Because according to the convention, if the action potential is moving away from the electrode, we will get a downward wave. So this is the action potential, this is the electrode we are concerned about. So this action potential is moving away from this, so we get a downward deflection. Now in the last step, what is happening? The action potential has crossed the second electrode and the second electrode, the area under the second electrode has repolarized. Now this is also positive, this is also positive. So the curve returns to the baseline. So from the downward deflection, the curve returns to the baseline. Okay, so we get an upward wave and we get a downward wave. This is known as biphasic because it has two phases. Okay, so this is how we get a biphasic action potential. This method is basically used for calculating or measuring the action potential in various parts of the body. For example, ECG measures the action potential for the heart, EEG action potential in brain, then EMG action potential for the muscles, then NCV action potential in nerves. Okay, this ECG is electrocardiogram, electroencephalogram, electromyogram, and nerve conduction velocity or nerve conduction studies, basically NCS. Okay, when you will do these systems, you will be taught about this in a little more detail. Okay, you don't need to know these right now. Just know that this biphasic, we were studying about the monophasic AP. So why do we need to study the biphasic AP? Because this principle is used for various clinical diagnostic tests. Okay. Now we will talk a little bit about injury potential. What does this mean? When a membrane is injured, normally what happens? This has plus everywhere. Now say a part is injured, this part is injured. Due to injury, the surface will show a negative charge. Okay, so a healthy area will show a positive charge on the outer surface, while a unhealthy or injured part will show a negative area. Okay, so what do we see? Normally what happens? When we place both recording electrodes on the surface of a nerve, we did not get any recording of membrane potential. We just saw this in biphasic AP. While measuring biphasic AP at rest, there is no potential measurement and no deviation of the curve. But when one is placed on the normal surface, first electrode, and the second electrode is placed on the injured part, we get a potential recording and a deflection. So this is positive, here we get negative. So we get a positive recording, and we just saw that a positive recording means a negative wave. So at rest, with one electrode on the injured part, in the healthy part, and one electrode on the injured part, we get a positive potential measurement and a downward wave. Okay, this is known as the injury potential. That is a potential measured between the healthy outer surface of a healthy part and the injured part. Okay, this was at rest. Next, what happens? A stimulus is given, stimulus is given, and action potential has reached the first electrode. So it becomes negative, and the injured part was already negative. So no potential is recorded between the healthy part and the injured part when action potential has reached the healthy part. So this will return to the baseline. Here we get a positive potential, here we get no potential recording. Okay, now what is happening? The action potential has reached a midpoint between the first and the second electrode. So the first electrode has repolarized. This is positive, this is positive. Sorry, this is positive, this is negative. So again we get a positive potential recording and a downward wave. See, positive potential recording, positive potential and a downward wave. And now when the action potential reaches the injured part, it stops. It does not cause any more change because the tissue is injured. It does not propagate the action potential or do anything basically. So this stops. Okay, so this stops. Okay, this was about the injury potential, where we see when we place both the electrodes on the surface, one on the healthy part and one on the injured part, we get a monophasic action potential. Now this has a role in diagnosing in the injury of various tissues, mainly the ST changes in myocardial infarction in ECG. Okay, ST segment changes in acute myocardial infarction in ECG. Okay, so this is just know that ST change, this actual injury potential has a clinical role. Okay, you will be taught about this ST changes and action potential, acute myocardial infarction changes in ECG later. Okay, so this was about injury potential. So the final topic, compound action potential, you don't need to know much about this, just that up till now we were talking about the recording on a single nerve fiber. But in outdoor clinical practice, or most clinical practice, we measure the action potential of a nerve, okay, of a whole nerve, not a nerve fiber. And a whole nerve is made up of many nerve fibers. So one nerve is made up of many nerve fibers, and each of these nerve fibers have different properties. Like they have different threshold, different conduction velocity. Okay, so they have different properties. Since they have different properties, they will give rise to different action potentials. So when we place the electrodes on the surface of the when we place an electrodes on a nerve as a whole, we get the summated effect of the summated action potential of all the nerve fibers, different fibers, which have different functions. Normally we would have got a one discrete nerve, but here we see we get a compound shape, okay, an irregular compound shape. This is because all the nerve fibers are not same. They have different parameters which gives rise to different action potentials, which then are shown in this way because they are summated and they overlap and give rise to this sort of wave. Okay, so this was compound action potential. It varies with the strength. Compound action potential can vary with the strength of the stimulus because different nerves have different nerve fibers have different thresholds. You give one strength, say you give S1 strength. S1 strength stimulates 5 nerve fibers and you get one shape. Now S2 strength will stimulate say 10 nerve fibers. So we will get another shape. This way, depending upon different strengths, we get different shapes. So with changing intensity, we get a changing action potential. Okay. And it also varies with the distance between the stimulating and the recording electrode because different nerve fibers have different velocities. Therefore, they show different recordings. The recordings depend upon the distance. Okay, if the distance, depending upon the distance, okay, if the velocity is more, the distance will be covered faster. If the velocity is less, the distance will be covered slower. One nerve has a higher velocity, it will cover the distance fast. One nerve has a lower velocity, it will cover the distance slower. Okay, so they will give rise to different sorts of action potential. That's why you get a compound shape in a nerve in real time. Okay, so this was all about action potential. You learned in the first class you learned about the resting membrane potential and the resting membrane potential, that is the membrane potential measured at rest. Then you learned what happens when you give a stimulus to an excitable cell. You will get electrotonic changes, then you can get a local response, and after that you can get an action potential. So we learned about all these and the action potential definitions. What is action potential? That is very important. Then the phases of the action potential, then the ionic basis of action potential, and finally we learned about the different properties of action potential like refractory period, accommodation, Rho-based, Chronaxi. Okay, and we learned how this action potential after formation is propagated. What happens, and we also learned what happens if a part of the nerve is injured, what type of action potential we will get. Okay, and finally we learned a little bit about the compound action potential. You will learn a little bit of the applied when you do the different systems, mainly when you do the central nervous system. You will learn about NCV, that is nerve conduction studies. When you do a cardiovascular system, you will learn about ECG, electrocardiogram, and when you do CNS, you will learn about electroencephalogram. Okay, these are all due to action potential recording. Okay, so this was a very difficult topic. I just taught you the basics. This basically action potential and membrane potential and action potential are a basis of physiology. You really need to understand this. Okay.